Okay, we've got the notes for section 5.4, which deals with modeling and optimization. So these are all word problems, finding maximum or minimum amounts, things like that. So here's our strategy. So understand the problem, read it carefully, identify the information you need to solve the problem, develop a mathematical model of the problem, draw pictures and label the parts that are important, introduce variables to represent the quantity that can be controlled, write a function whose extreme value gives the information sought, graph the function. So oftentimes you use the graph to find the maximum or the minimum value. Excuse me. Identify your critical points, so set the derivative equal to 0. So you solve the mathematical model, show the result with another method, and then interpret the solution. So there's not really, though, a hard and fast rules for doing these problems. So we'll just look at the examples. Find two numbers whose sum is 20 and whose product is as large as possible. So we'll call my number 1 is just going to be x. Now my second number, if they have to add up to 20, is whatever 20 minus x is. So those are my two numbers. Now I want to make the product, which would be this equation, as large as possible. So this is 20x minus x squared. So what I can do is, if I'm looking for a maximum minimum, I can look at, so this is my function. If I find f prime, which is 20 minus 2x, set it equal to 0, it gives me a critical value. So 10. Now this is bounded because the smallest, well, I guess technically it doesn't have to be between 0 and 20, but since we'll talk about positive numbers. So between 0 and 10, so we'll say we'll plug 5 in. If I plug 5 into my derivative, I get a positive number. If I plug like 15 in, I get a negative number. So that means this product rises and then falls. So at x equals 10, I have a maximum value. And if the first number is 10, so this is my n1, n2 is also going to be 10. This also kind of works a lot when you see geometry problems or area problems. If you need to maximize an area, typically a square does the best for a given perimeter amount. Okay, example 2, a rectangular is to be inscribed underneath one arch. So we're going to draw a rectangle underneath an arch of a sine curve. So sine starts at 0, one arch ends at pi. So if I want to maximize the area, I need the equation for the area. So the area is equal to length by height. Well, the height is just the value of sine. So that's not too bad to find. So sine x is how tall my rectangle is going to be. The trick is figuring out the width. So if this point here is at x, if you notice it's mirrored. So this whole width is pi, and I'm coming x in from each side. So that's my equation. Now, I can do this a couple ways. This algebraically isn't going to really be very easy. I could distribute, make it pi sine x minus 2x sine x, and do derivatives. So do a prime equals pi times the cosine of x. This is going to be minus 2 sine x minus 2x cosine x. So I could look at where the derivative is equal to 0 and find my critical points, or I could look at just the graph of a and figure out where the maximum is. So now notice that x can't be any more than pi over 2, because if x gets to be pi over 2, I don't have a rectangle because I'm coming in from both sides. So let's look at just the graph of a. So pi sine x minus 2x sine x. Okay, well, let me zoom auto. Nope, probably didn't want auto. Let's do view windows initial. That's probably the better bet. So there we go. So if you look, we're only looking between 0 and pi over 2, which is about 0.57. I feel like my graph was wrong. Oh, sorry, pi over 2 is 1.57. Sorry, so pretty much between here and here-ish. If you notice, there is a maximum right there where my cursor is scrolling across. So my calculator, gsolve max. Now it's going to find all of them. There's the one I want. So there's a maximum when x is 0.71, and the area what is the largest area the rectangle can have? So that's the y value. So the area would be 1.12-ish. If the x value is 0.7, so it's 0.7 by the sine of 0.7. So call that my length. So my width is going to be 0.65. So that's how you can find the dimensions.
You can just look at the graph. Now, if I'd graphed the derivative, I would have solved for where it's equal to 0, because I want to know where the critical numbers are. So. Oh.
That's not actually the length of the rectangle. Sorry. That's this distance here. So I need to plug this part here is the length by height or width or whatever you're going to call it. So the actual width, if x is 0.7, is pi minus 2 times 0.71, which is about 1.72 is the actual answer. I found out how far in from the edge I was, but the question actually wants that amount, which is the 2 minus, or pi minus 2x. Okay, so business and industry. So we have an open top box made by cutting squares of side length x from the corners of a 20 by 25 inch sheet of tin and bending up the sides. How large should the squares be to make the box hold as much as possible? So essentially what's happening is I have a sheet that's 20 by 25. I'm going to cut corners of x out. And when I fold, it's going to give me a shape that looks like this. So an open top box. Now this front edge was 25 inches long, but I cut 2 squares out of it. So this distance is now 25 minus 2x. This edge here was 20 inches long, but I cut 2 corners out of it. Now the trick here is the height of the box is if you think about what the shape's going to do, if I fold on the large dashes, these cuts that I make are going to become vertical. So the height of this box is actually vertical. So the volume of this box is length by width by height. So how large should squares be? Okay, so I need to clean this up. So I'm going to multiply, FOIL the first two together. So 25 by 20 is 500 minus 50x minus 40x plus 4x squared. If you work the FOIL out, there's still the x here. So distribute the x through. I'm going to distribute and do like terms and put it in the correct order. So 4x cubed, that would be negative 90x. This become negative 90x squared plus 500x. So that's the equation for the volume. So if I want to maximize the volume, I need to know where the critical values are. So 12x squared minus 180x plus 500. So that's a quadratic. I'm going to let my calculator handle it though, because it has a lovely equation solver, and I don't want to do the quadratic formula right now. Polynomial degree 2, 12, negative 180, and 500. So there are 2 solutions. X is 11.32 or X is 3.68. However, only one of these is actually valid, because if you, we'll plot a number line here. The smallest cut that I can make is 0. The largest cut that I can make is actually 10. Because if this side is 20, if I cut 10 inches from each side, I cut the whole side off, which means I can't plot that. So 3.68 is the only value I have. So I need to choose some number less than it, some number more than it, and then figure out what the signs are. So like we'll use the first derivative for 1, and we'll say 4. So if I plug 1 into the first derivative, I get 12 minus 180 plus 500. So that is a positive number. If I plug 4 in, I get 12 times 16 minus 180 times 4 plus 500, which is a negative number. So that means my volume function rises and then falls. So when x is 3.68, I'm going to have a maximum volume. So that's my size. What is the resulting maximum volume? To do that, I plug x back into my volume equation. So that's going to be 25 minus 2 times 3.68 times 20 minus 2 times 3.68 times 3.68. So the volume of the box is, doing inches, so x is that, which means the volume is inches cubed. So the biggest box that I can make is about
820 and a half cubic inches in volume. Is the most I can hold.
All right, 4, you've been asked to design a 1 liter, so just a note, 1 liter is 1,000 cubic centimeters. Shaped like a right circular cylinder, so the volume of the circular cylinder is pi r squared h. Least material is referencing the surface area. The surface area of a right circular cylinder is 2 pi r squared plus 2 pi r h. So I want to minimize that function. Now the problem is, as of right now, I have too many variables. So I need to solve this volume equation because I know what the volume of the can is. And I'm actually going to solve it for h so I can replace this h. So h is 1,000 over pi r squared. What that means is that the surface area can be written as 2 pi r squared plus 2 pi r times 1,000 over pi r squared. So we'll just replace h with h. Doing a little clean up, this becomes 2,000 over r. 2 times, okay. So this is s. Now, all right, so if I want to find a minimum, we'll take the derivative. So this is going to become 4 pi r. This is the same thing as r to the negative 1, so it's negative 2,000 r to the negative 2 when I do the derivative. I want to know when is this equal to 0. So what I'm solving is, we'll turn this back over. So I'm looking for that. Now, I don't want to algebraic do this, so we'll look at the graph. We're going to use 4 pi x, because your calculator doesn't understand, minus 2,000 over x squared. Draw. So you can see there's 1 0 there, so gsolve root. So r is equal to 5.42. And if you look on your number line, so once again, your radius has to be more than 0. 5.42 would go here. Now, if you look at the graph, I can tell it goes negative to positive, which means here this graph is falling, then rising, which means this value right here, oops, off the screen, is a minimum. So using a radius of 5.42 will give me a minimum, which means that the height I still need to figure out, but I can do using this equation for height. So 1,000 divided by pi divided by 5.42 quantity squared is 10.84. Now, just a note, if that's that, the can that will have the given volume and minimize the surface area, the diameter and height are actually the same. So the can is just as wide as it's tall. Okay, examples from economics. So the derivative of R is referred to as the marginal revenue. So it's the revenue you gain from selling one more item. dC dx, or C prime, is a marginal cost. And then dP dx is a marginal profit. So gross versus net. So the maximum profit, if there is one, occurs at a production level in which the marginal revenue is equal to the marginal cost. So next problem is going to ask about that. So suppose that R of x is equal to 9x and C of x is equal to x cubed minus 6x squared plus 15x. Thousands of units is their production level that maximizes profit. So that's going to occur when R prime is equal to C prime. So 9 is equal to 3x squared minus 12x plus 15. So we'll move everything over. This is quadratic, minus 12x. So if I subtract that across, I get negative 6. I can divide everybody by 3, but I'm not sure that's going to help. Not really, still not factorable. So I'm going to let my calculator handle the solutions. So equation solver, polynomial second degree, 3, negative 2, 12, negative 6. Whoops. So there are 2 values here. So one production level is 4.45 thousand units, and the other one is, which doesn't actually make sense, because you can't make
negative units. So it's gotta be that positive one, is the only one that should work, unless they've done,
Oh, yeah, I did. That's a positive 6. I was gonna say I didn't think that made sense. So let's make this positive 6. Let's see if we get two actual, there's two valid solutions. So x is either 3.41 or x is 0.56. Now we have to figure out which one it is, so we need to plug in. So just make sure that r is more than c. Because if r is less than c, we have an actual maximum loss. So when x is 3.14, 9 times 3.41, sorry, is 30.69, and 3.41 cubed minus 6 times 3.41 squared plus 15 times 3.41. So that's a positive number. So this is profit. If I plug this one in, I'm actually going to get a loss. So if you 3.41 thousand would be the same thing as 3,410. You'd multiply by 1,000 units. The profit is 2103.
per unit, I assume. Yeah.
Okay. The last one down here, minimizing average cost. It says the production level, if any, which the average cost is the smallest, is the level at which the average cost is equal to the marginal cost. So average cost is given by taking your cost function and just dividing by x. Because the cost function tells you how much it costs to make x units. So average would be total amount of cost to make x divided by how many you make. So we're going to solve this equation, c prime of x is equal to c of x over x. So c prime of x would be 3x squared minus 12x plus 15. C of x over x is actually just going to cancel an x out here. So x squared minus 6x plus 15. So I'm solving this equation. So everybody comes to one side. So 2x squared minus 6x, and it's going to equal 0 because the 15s are going to cancel. So I can factor a 3x out, not a 3x, sorry, a 2x out, which leaves me x minus 3. So at x equals 0 and at x equals 3. So this one is technically accurate, but it's also common sense. If you don't make any items, your cost is going to be at a minimum because it's going to be $0. You're not manufacturing any. So there is a production level. When you are making 3, in this case, 1,000 units. So you have to be careful. So. And that brings us to the end of this section.